Hello, so we're going to look at, this is unit 10 that we're on. We're going to be doing inference, which is confidence intervals, and hypothesis testing with numerical data, so dealing with means instead of proportions. Today we're going to focus specifically in on confidence intervals, so a one sample interval for means. Before we even get into anything dealing with the mechanics of it, the math and the interpretation and all of that stuff, we're going to have to talk about how we deal with means a little bit differently, starting with a little guy named William Gossett. So William Gossett lived from 1867 to 1937. He worked for Guinness, the Irish beer company, so not Guinness World Records, but for the beer company. He worked in quality assurance, which easiest way to think of that is taste tester, but it was a little bit more complicated or complex than that. He was a statistician who used statistics to help the company create the best tasting beer. He used the pseudonym student in all of the papers that he produced or published while he worked there because Guinness didn't want their employees to publish papers using their own name. So even though he was talking about statistics in his published papers and not beer, he still had to use the pseudonym student. So everything that we used that came from his research and his study was known as the student for a really long time until it kind of came out with who he was. But what he discovered, or what student discovered. So at his job, he taste tested batches of dark lager in very small sample sizes. He set his level of significance, his alpha, so that he should only be rejecting good beer about 5% of the time. So he set his alpha at 0.05, so his probability of a type 1 error, which is rejecting good beer, should happen 5% of the time. But he later found out that he was actually rejecting good beer closer to 15% of the time. So something was going on, and he kind of realized that the normal model, which is what we've always used, doesn't work quite as well with smaller sample sizes. And more specifically, what this means for us is that we are not actually using the normal model most of the time for a means problem. We're using something called a t-distribution or a t-model. More specifically, they were known as the student's t-models because that was his pseudonym. So the student's t-models, they still look, if you were just looking at a t-distribution without really thinking about it, you probably still call it normal. It's still unimodal, it's still symmetric, but a normal model has a very specific curvature to it that a t-model doesn't quite match up. So a t-model is going to be shorter in the middle and kind of more spread out to where the tails have a little bit more area, and typically, a t-distribution is going to go for more standard deviations in either direction. So there's more area in the tails, and the reason for that is because we are using a sample standard deviation to estimate a true standard deviation. In real life situations, we're probably not going to know the population standard deviation. We're using what's true for the sample to make some kind of estimation about the population. So because we don't know that true population standard deviation, we only know what's true for a sample, that leads to a greater amount of uncertainty. So not only do we not know the true mean, but we also don't know the true standard deviation. So there's an extra layer of uncertainty or variability with a means problem because of that. More crazy than that is that technically there is a slightly different shaped t-distribution for every possible sample size. So this graph kind of shows like our normal model is this one that's the tallest in the middle and the shortest along the sides or along the edges. If we have a t-distribution with 20 degrees of freedom, which just means a certain sample size, it's a little bit shorter in the middle and a little bit more spread out or a little bit taller on the sides. T-distribution with 10 degrees of freedom is even shorter in the middle and even more like tall and spread out and more area along the sides. Degrees of freedom is actually how we identify which t-distribution we're going to use. It's based on sample size and sometimes a couple other things. I could spend probably a whole day or more talking about degrees of freedom and what it means, but also how or why we use it in problems like this, but we just don't have time for that. So just know that degrees of freedom is related to sample size, and it's how we identify which t-model or t-distribution we're going to use. For what we're doing right now for a one sample confidence interval or for a one sample hypothesis test, if we just have one sample of data, not two. Degrees of freedom is just n, so sample size minus 1, and it's that simple. But it does get more complex than that if we're dealing with multiple variables or multiple samples. But for now, it's just n-1. If you are curious, I'll put this link on the calendar as well, but there's a video, it's a crash course video that looks a little bit more into degrees of freedom and what it actually means. But for the sake of our class and our problem, we're going to leave it there and just realize that it's a way to identify which t-model we're going to use. So the question is, kind of where I want to lead, is when do we use a t-model or t-distribution instead of a normal model or a z-distribution? So where it comes from, the biggest thing I want you to remember is we do this when we don't know the population standard deviation. In other words, it's when we're using the sample standard deviation to estimate the population standard deviation. And that's going to be pretty much always. In real life, we don't know the true mean of the population. Why would we just happen to know the population standard deviation? If we knew that, we probably wouldn't need to do a confidence interval or a hypothesis test if we knew that much information about our population. So most of the time, especially in real life, we are using a t-distribution because that's what we've got. Other things that are good to know about the t-model or the t-distribution, one is that, again, they have more area in the tails. They're more spread out, which means that the tail areas are going to have just more space there. Another thing that is good to know is that as degrees of freedom increase, the t-model or t-distribution looks more and more like the normal model. And in fact, a t-model or t-distribution with infinite degrees of freedom, infinite sample size, would look exactly normal. And that's going to lead me to our t-table. So t-table, I did just recently attach that to the little ringed formula chart table situation that's hanging on the wall by the door. So if you didn't grab one on your way into class today, then make sure you grab one. If you still have the yellow tables that I gave out last semester when we first started talking about normal model, the t-table is on the back of the z-table, so it's table B. But if you don't have either of those things, it is available on my website. So if you go to this AP Stat website under More and then go to Tables, that will open this lovely file. This is actually what the table you get on the AP exam will look like. It's a little bit more spaced out. They kind of spread out so the numbers weren't too tiny. So those first 4 pages are all Z-table, just really spread out. And then when we get to this page, it's table B. This is the t-distribution table. So we've got that. So as I mentioned earlier, we have technically a different t-model, different distribution for every possible degrees of freedom or sample size. So how we identify that on the table, along the left-hand column, you'll see the letter degrees of freedom, DF. So each row in this table represents one t-model or one distribution. But they had to really seriously kind of condense that model. Technically, we could have an entire z-table worth of numbers for every possible row in this table, every possible degrees of freedom. But we couldn't have that. That would be too much paper. So they condensed it down to one row per model or per degrees of freedom. So if I were to read this table, so I'm going to look at t-table practice. Let's say I was doing a confidence interval and I needed to know my critical value, which is, we called it Z star, Z asterisk before, but now it will be T star, for 98% confidence with degrees of freedom of 10. So I needed that for my formula or to answer a question. So the way I'm going to do that, if you remember when we did it with Z model, with a normal model in the last couple of units, I first had to kind of make this graph, at least in my head, and I thought, okay, 98% confident means I want 98% in the middle, right? So then there's 2% left over, but that has to be split into both sides, so I need each little tail to have an area of 0.01, and 0.01 is what I would look up in my z-table to find the z star or z-score that I needed. So I still have to do that process, that thought process to an extent. But now what I'm going to do on my t-table, along the top you have different tail probabilities. So I want my tail probability to be 0.01, and then I'm going to go down to the row that is 10 degrees of freedom. So 10 degrees of freedom, 0.01 is my tail probability, so my critical value, my t star, for that problem would be 2.764. So that would be my answer to this one. So t star is 2.764. So the next one says I'm still going to be 98% confident, so my tail area stays the same at 0.01, but now I have a sample size of 20. And remember, we don't identify which row to use based on the sample size. I use degrees of freedom. So if my sample size is 20, degrees of freedom for a one sample procedure is just sample size minus 1, so 19. So the row I'm going to look up on my table is 19. So looking at my table, I'm still dealing with that tail probability of 0.01, but now I have degrees of freedom of 19. So I would go down to that row, and my t star, my critical value, is 2.539. So that would be my critical value. So now I'm going to show you a couple of little fun facts about the t-table. So we do have our tail probabilities up at the top, so I can do it that way. But if I scroll all the way to the bottom of my t-table, I will see a confidence level. So I used 0.01 for the tail probability, but if I go to the very bottom, I should see 98% confident. So it actually tells us which confidence level belongs with each column, so that makes things a little bit faster. We don't have every possible confidence level here, but we have most of the ones that you're going to see. And to be honest, you should never see problems on an AP exam that uses anything other than these for a means problem, because then it gets too complicated to find the actual t-star that you need. So 98% confident, and then we go to whatever degrees of freedom we need. The other thing I wanted to mention is that earlier when I was talking about facts about the t-distribution, I said that as your sample size increases, as your degrees of freedom increases, it looks more and more like the normal model. And in fact, a t-model with infinite degrees of freedom is exactly normal. So we do have a row on our table that is labeled with infinite degrees of freedom. So that row right there actually represents the Z or normal model. So if I wanted a critical value for a Z star instead of T star, I could use this row. So for 95%, the Z star is 1.96. For 98%, the Z star is 2.326. For 99%, the Z star is 2.576. So this would have been a really quick way to get critical values in our last couple of units when we were dealing with the normal model and Z star for proportions. I just didn't tell you about it, so now I'm telling you about it. There's our Z stars on the very, very bottom row. But in this unit, we will pretty much always be using T star. So that is how we use that table to find that information. The next couple of videos, I'm going to go through some of the other important information, and then we'll get into an example problem, putting this all together to do a confidence interval.